By the early 1900s, chemists were already looking for new and innovative ways to turn nitrogen from the atmosphere into fixed nitrogen suitable for use in fertilizer, refrigeration, explosives, and plastics. In 1908, Fritz Haber discovered a method for utilizing high temperatures, high pressures, and iron catalysts to synthesize ammonia from gaseous elemental nitrogen and hydrogen, which were cheap and abundant materials. Carl Bosch would subsequently improve on this method to make it feasible for production on an industrial scale. The resulting system is known today as the Haber-Bosch process. While the Haber-Bosch process would prove essential to large-scale food production, it also led to a few extremely detrimental consequences. Firstly, such a dramatic increase in food production efficiency is often credited as the instigator of the massive population increase in the last century. Likewise, the continual and excessive use of nitrogen fertilizers results in increased greenhouse gas emissions into the atmosphere and a loss of biodiversity in plants. Furthermore, the fixed nitrogen ammonia produced has been used in the past 100 years to create powerful and violent explosives in warfare, leading to the deaths of thousands. Our first reactant is nitrogen gas, or N2. N2 consists of two nitrogen atoms connected with a triple bond, as shown in its Lewis dot diagram. Each nitrogen has one lone pair of electrons which aren't involved in bonding. The hybridization for each nitrogen is sp1. This is because they have one bonding domain and one lone pair. Under valence bond theory, the triple bond consists of one stronger sigma bond and two weaker pi bonds. The second reactant, H2, consists of two hydrogen atoms bonded with a single bond, each with no lone pairs. Ammonia has three hydrogen atoms single bonded to one nitrogen atom, as shown in its Lewis dot diagram. NH3 is a polar molecule with a trigonal pyramidal geometry, since its steric number is 4 and it has one lone pair. The nitrogen is sp3 hybridized since it has three bonding domains and one lone pair. According to valence bond theory, it makes a sigma bond with each hydrogen atom. Molecular orbital theory allows us to visualize the organization of electrons into orbitals of increasing energy. Subsequently, the bond order of H2, calculated by subtracting the number of electrons in antibonding orbitals from the number of electrons in bonding orbitals and dividing the difference by 2, is 1. As seen in the diagram, the HOMO of H2 is the sigma 1s orbital, and the LUMO is the sigma 1s antibonding orbital. Now looking at the MO diagram for nitrogen gas, the bond order of N2 is 3. As seen in the MO diagram, the HOMO of N2 is the sigma pz orbital, and the LUMO is the pi star orbital. Because the difference in energies of nitrogen's 2p and 2s orbitals are less than 13 eV, there is orbital overlap between the 2pz and 2s orbitals of N2.
We're now going to identify the non-covalent interactions of the products and the reactants, as well as the properties that contribute to these interactions. Diatomic nitrogen contains a non-polar covalent triple bond. This bond is very strong because of its short bond length. Because diatomic nitrogen is a non-polar molecule, the only non-covalent interaction it will participate in is the formation of an induced dipole. These temporary dipoles are called London dispersion forces. Hydrogen is also a non-polar, covalently bonded diatomic molecule, so it too only participates in London dispersion forces. Ammonia, however, will participate in more non-covalent interactions. Ammonia can make hydrogen bonds with itself because the three hydrogens bonded to the central nitrogen atom allow the nitrogen to act as a hydrogen bond donor, while the lone pair of electrons on the nitrogen atom can serve as an H-bond acceptor. Also, because of the electronegativity difference between hydrogen and nitrogen, with the delta En equaling 0.84, ammonia is a polar molecule. Since the nitrogen is more electronegative, it will bear a partial negative charge, while the hydrogens will bear a partial positive charge. As a result, it will participate in dipole-dipole interactions with itself and other molecules. Of these, the hydrogen bonds are the strongest non-covalent interactions. Next, we will discuss the transition state for this reaction. As you can see in this image from Spartan, as the three hydrogen bonds are forming, the triple bond in the diatomic nitrogen is breaking. Hammond's postulate tells us that, because the Haber process is exothermic, the transition state will resemble the reactants more closely than the products.
The next section is the thermodynamics and kinetics of the reaction. The change in standard enthalpy of formation is the standard enthalpy of formation of the products minus that of the reactants. The standard enthalpy for ammonia is negative 45.94 kilojoules per mole, while the standard enthalpy of both reactants is 0 kilojoules per mole. The change in standard enthalpy is negative 91.88 kilojoules per mole. Because there is a negative change in enthalpy, the reaction is exothermic, meaning it gives off heat. The change in entropy for the reaction is the difference in entropy between the products and reactants. The entropy of ammonia is 192.77 joules per Kelvin. Entropy of the reactants is 191.609 joules per Kelvin for N2, and for H2, it is 130.68 joules per Kelvin. The change in entropy is negative 198.109 joules per Kelvin. Because there are 4 atoms in ammonia, the molecule has 3 N, or 12 degrees of freedom, associated with the possible energy arrangements of the system. The Gibbs free energy for this reaction depends on the values of delta H and delta S, along with the temperature of the reaction environment. The standard temperature is 298 Kelvin. The negative Gibbs free energy value means the reaction is spontaneous.